Right, please.
Okay, so I'm going to say about polarization signature of coronal cavities in CoMP and UCoMP, mostly from CoMP, but I will also show some nice example of new observation and what we can see. So a few words about cavities. Usually we see cavities as a part of the coronal mass ejection. We can see on the left bright front, dark cavity, and the bright core. But on the right side, you can see the quiescent structure with helmet streamer, with dark cavity and quiescent prominence. Cavities are a dark region of rarefied density with elliptical cross-section. They are observed in wide wavelength range from the radio to soft X-ray. And you can see a very nice example of the cavities observed by AIA 193 angstrom. We analyzed thermal properties of coronal cavities. Such analysis was made by many authors, but they received different results. So we analyzed 33 cavities and applied differential emission measure methods. We analyzed several cavities observed during maximum and several cavities observed during minimum of solar cycle, and measure temperature of the cavities from the DEM method, and we measured also the average temperature of the coronal streamer at the same height. And on the left, you can see some results. Temperature of the cavities was always higher than temperature of the coronal streamer, and it was also higher during maximum compared to the minimum of solar activity. We've got a lot of information with the CoMP observation, because from the CoMP, you've heard a lot of information about CoMP today. So you can see field of view. So we had information about magnetic field, plasma density, and motion. But for us, the most important was motions. So we analyzed Doppler velocity, and we analyzed linear polarization signature. So a few words about the line of sight flows. The first observation with CoMP was published in 2009, but later on we found that when we analyzed cavities, we see such nested ring-like structure. You can see it on the left. There are 3 cavities day by day, and we can see how the structure can change and how can we observe these flows as a nested ring-like structure. And on the right, you can see several other examples. This is another paper, but we noticed that, in fact, if the cavity is oriented towards us, we always see such structure. So sometimes it's when I open, for example, the web page of the CoMP and try to find new example, I always look at the Doppler velocity. This is the first sign to have the good orientation of the cavity. And we, of course, found a lot of nice results in linear polarization, because you can see now AIA 193, but look at this feature in linear polarization. We call them lagomorphic structure because they look as a head of bunny with ears, with hair. And if the cavity is high enough, we can see whole structure. But I will show you later even better example. In this first paper, we analyzed only 68 different individual cavities, but my students later on analyzed the whole data. And how can we interpret this results? We used forward modeling, And on the left side, you can see, you don't see my, oh yes, you can see it. This left panel show AIA. These are CoMP observation in linear polarization, and this is the model. I will not tell you more about this because Sarah has a talk and she will explain everything, what we can see. But even now you can see that the model matched to the observation very well. And to do this model, we used UHOXFAM simulation with the flux rope, and we could explain such observation with the flux rope model. And on the right, you can see that we can also compare the width of the structure. On the left, AIA, on the right, linear polarization. These are profiles. These are polar angle cuts through the cavity and through the lagomorphic structure, and we can define the width and show that it matches to each other very well. So my students analyzed whole CoMP data between 2012 and 2018. So all the data we could find, she analyzed, and she tried to find as many lagomorphic structure. And in the table, you can see that she analyzed more than 500 individual cavities, but every cavity, in fact, was observed for a few days. So she analyzed, in fact, 2,000 cavities if we counted day by day, but it was more than 500 individual cavities. And this is the most important results here. Okay, sorry. 82% of cavities were associated with this characteristic structure in linear polarization, but it doesn't mean that 18 other percent not. We just do not have data for that. Sometimes we observe cavity only for 2 days, sometimes 3, 4, and so on. But if you look at this bottom plot, you will see that if we observe long enough, we always see this lagomorphic structure for at least 1 day. We had several cavities observed for 10 days or even more, and we always had lagomorphic structure there. And of course, if we had less observation, there was more chance to not observe lagomorphic structure. Why? Probably because of the one reason could be, I don't know, that quality of data, or for example, orientation of the structure. And we try to check it, how visibility of the lagomorphic structure depends on the orientation of the structure. And we applied forward modeling once again. And at the top left, you can see unrotated structure. So we can see our lagomorphic structure. And the last plot is structure rotated with 15 degrees. And so such rotation makes our lagomorphic structure, in fact, invisible. So if we have less observation than, I don't know, 5, 6, 7 days, there is a chance that the orientation won't be so good to observe lagomorphic structure.
I make a really quick comment about that, because these are like tunnels and they're lying above a neutral line. So if your neutral line has a bend in it over the course of the few days when that long quiescent filament rotates past the limb, you might go transition from favorable to less favorable orientation.
Yes. Yeah. So we also check the relation between cavity width with different observations. So on the right, there is a cavity width from SDO and the CoMP. And we see that the correlation is very good, but the correlation is still visible between cavity width with SDO or CoMP-R and structure in linear polarization. Okay, so now let's go to the UCoMP observation. I will show you some nice example, and as you can see, this is the same structure. So UCoMP it's IN13. So we see two cavities on this day and this structure in Doppler velocity, but also our lagomorphic structure at the bottom part. And we also we can of course also make some cuts through the cavities and linear polarization structure and Doppler velocity and check the profile, so we can see that the width also match very well. But this is a very nice example that you can see very strong flows just in the middle of the cavity, and it's very well correlated. So the center of the cavity here, we have some substructure here. It's connected with the strongest flows in the Doppler velocity line of sight flows, even 15 kilometers per second. I haven't seen such strong flows before.
Are there counter streaming flows there? Do you think?
Yeah,
It looks like it.
I will show you more such plots.
Is there
So
any way to get rid of that box in the bottom right so we can see?
There might be on the.
yeah, but I cannot do this. I cannot.
Okay.
Yeah, okay, I think
So we'll figure it out. Keep going.
But also the counter streaming flows, yeah, but
Yeah, we discuss a lot of it. We don't know because we don't know this. There's zero. But if you look at this plot now, you can see that outside the cavity, the signal are very close to the zero. So I believe that the 0 point now it's we don't see the shift outside the cavity. But I have more plots.
and even if we don't know the 0 point, we don't know if they're counter streaming, but we know there's a strong gradient.
Yeah.
That's for
Yes.
sure.
So in the previous paper, we didn't analyze absolute values of velocity, but we always discuss the relative
Thank you.
velocity. Here, for example, I think that it's quite suspicious because almost all signal is below the zero. So I would say that we can check.
Yeah, I'm looking at the 29, and if you look at the East link is it's all blue.
Yeah.
And it's not rotation because the velocity that you see there are like 5 kilometers per second, so they're definitely larger than rotation. There is a stray light effect that Ben was mentioning before. So unfortunately, some of these systematic errors, some of these issues show up more in higher level product like velocity and line width. Line width is particularly sensitive to that, but also velocity.
Yeah.
So I don't think it's a zero.
Yeah.
0 point,
But
not necessarily, but certainly there are some systematic.
Yeah. But at least we can say that we still have some gradient with
Oh, yeah. The gradient is believable.
Yeah.
I mean, that's
absolutely.
but
So-
the absolute value,
Yeah.
it's a little bit.
Another day we can see Doppler structure, Doppler velocity, linear polarization, and there are again some profiles.
This is the next day? Or
Yes, this is another day, not next, but 23 January. So and you can see also Doppler velocity. So it changed again. Another. Okay. Two others days, so February 7 and February 17, and also profiles. For example, here I think that it's also we can see some trend in the Doppler velocity. So, but the other profiles are absolutely the same as we obtained earlier with the CoMP. So the width of the structure. Yes, please.
Shahida?
Hi. Do you think that any of these cavities ever erupt when they are in UCoMP's field of view?
I not this one because I checked it. They are at polar crown region, but I will show you later the example of eruptive cavity.
Sure. Yeah. Thank you.
So another example of for example, here, we absolutely should believe that the gradient changed from -4 to +4, but without the knowledge of 0.
Yes.
So the relative velocity is 8 kilometers per second. Yes. Okay. Another example. So we have a lot of such examples, so I will show you only a few ones. And it looks the same if we look cavity by cavity. Another one, and also the velocity change from -5 to +4. Okay, and this is a very nice example of pseudo-streamer. We have also more such observation.
What day that is?
August 6th,
August 6th.
August 6th, 2022.
Thank you.
Okay, so now that
Go back up, just
this is not the same scale because I made AIA on other days, so
okay.
it's not exactly the same, but you get the same structure.
Yes, thank you.
Okay.
And Mike, and also tomorrow when I'll talk about the magnetic models that you forward model.
Yeah, that's why I'm not talking about modeling at all. So Sarah will tell you more. I just want to show you some nice example. So why UCoMP? Because of the field of view. This is the example of erupting cavity. And we have, of course, AIA data, but this yellow box show you the field of view of AIA. So in this case, we see with AIA only half of the structure. And that's why we need UCoMP. Yes.
Middle correct.
Yeah, so these are plots from the web page, but you can see that on the right we see linear polarization. Probably the X point we've already modeled for higher cavities. So this is very good example of a huge cavity, which is impossible to analyze with other instruments. We need much larger field of view, like with UCoMP. These are observations from 23rd and 24th of October. So we can see that this lagomorphic structure is still visible, although we have some eruption meanwhile. And 25th and at 26th, there was a final eruption and the structure disappeared. So for this particular case, we can see the moving. And at the end of the day, you can see the eruption. Oh, that's all. So we saw only the beginning of the eruption. With AIA, it's of course easier because we have observations all the time.
Wait,
So-
can I ask a quick question about
Yeah.
that? Because it's something we can dig into during the practicum. There's like a data jump, and I think it's because the observing programs shifted, right?
Yes.
So maybe there are data that can be retrieved from level 1 that can fill in the gaps.
Probably not.
So
It depends on why it jumped, but, so we probably went and looked at 706 and 637 during that jump.
Oh, we might be able to, well, I mean,
So we,
You can. Maurice had, but not consistently. Maurice had some movies of the different lines. They're all taken at different times.
yeah, but you could fill
Yeah,
out a
but piece it
timeline with the different
together.
lines. Yeah, exactly.
Yeah,
That could be something that'd be interesting to kind of try to play with.
yeah, but you can't see as far out. It's been pointed out by
Yeah,
every
that's the
speaker
issue.
we've had.
79 would be the best feeling because you see
As close as, yeah.
but it's gonna,
And then
Come in
789.
right when, after 1074, so you're not gonna get, there's gonna be a 30-minute gap with no data point in it if you're only
Yeah.
1079, 1074 there.
But it still would extend a little bit that gap. So this is an example of, to let people know
Yeah.
that if the level 2 products can't get you everything you need, there's a way to create, customize things to analyze an event. That's sort of thing we can talk about in the practice.
Right?
In fact, as a catalog, the date that shows exactly what was observed at what time and how many wavelengths is really available for people to see what the program was for that day. It maybe also sometimes there is a gap because there are clouds and there's something that the observer are doing, maybe a vibration or something else. And there are the observer logs also available online. They're already available that people can go and look. If you have a day that you're interested in, I really encourage people to look at the observer logs because they have interesting information like clouds are coming in or winds or stopping the instrument because of a problem. So you can see that in the logs that is all available.
When we talk on Friday, I mean, Maurice was talking about a CME observing plan that presumably in theory, it could be triggered by the observers saying, oh, something's starting, let's try doing this thing. But there might be different CME observing plans depending on whether it looks like it's coming from an active region or a cavity. The cavity, the polarization is really interesting.
I'd be wary of something that says, wait till you see the actual event in progress and then switch over. It's gotta be, these are the things where we expect to trigger a thing, and let's observe in that way there.
Anyway, sorry, I'm just letting you know.
One.
Oh,
I need 1 minute. Okay, so for this case, I also applied DM analysis. So, but we can see only the bottom of the structure, not this huge structure visible with the UCoMP. But we can have such information. This is so the title of each frame. It is temperature in logarithmic scale. So this is the million Kelvin. The last plot is about million, but you can see a lot of eruption there. But this is very interesting because we have 10 millions here.
Sorry, this is DEM using AIA data, right?
Yes, this is from AIA. But at the beginning of the first eruption, we see plasma with 10 million. So we can analyze it more detailed, but only the bottom of the structure and not the whole cavity. And last two movies. This is the same eruption at the end of the day. Oh, here.
There's the jump.
Yes, there
But
was
still,
a
it's interesting because it looks like what you would expect with a rising flux rope.
Yeah.
And spoiler alert, that's what we think the model is.
yes. And the last one, okay, the last one will be now. This is the Doppler velocity. Wait until the end of the day up here. Okay, but such cavities absolutely good candidate to analyze CME because you have plenty of time at the beginning of the eruption. And in fact, we have such cavity observed by CoMP with 6 hours of observation. Okay, that's all. Thank you.
Yes, use CoMP. I think Maureen said that there was no other CME. She goes, well, there was that one. I said, yes, but we never published that one.
Question.
Yes.
Oh,
Shall I go ahead?
Yeah.
Okay.
So, did you stop the recording? Oh, sorry.
oh, are
Yeah.
we doing questions?
Was there a question?
Yes. Shall I go ahead and ask it?
Please.
Okay. Great talk, Ursula. So it gave a very good perspective of what UCoMP can do. And yeah, so I have a quick question on understanding how those cavities, the measurements that you do with the cavities, do you think the role of the solar rotation, that effect is removed in it?
With
If
this
it is-
flow,
Yeah, if it is a long tunnel of flux rope, then we can continuously keep seeing the cavity. If so, I see that you made measurements with the width of the cavities also, right? So when the sun is rotating, so that width might change. So do you accommodate that effect also?
we just check the observation day by day, and we notice that such structure are, especially in Doppler velocity, really, we can see the Doppler velocity, such structure in Doppler velocity in 5-6 days, not necessarily in linear polarization, but this is what we could model that we know why.
Okay.
Yeah, and there's the paper of Nishikata that is worth
Yeah.
looking at for sure, because if these things are visible on the disk, or she uses EUV limb observations to make Carrington maps, and Carrington maps latitude, longitude, and you can see them as tunnels that stretch out for sometimes like 100 degrees or more. I mean, so which corresponds to like 6 or 7 days, which is what Liz talking about with these limb observations. So they can be extremely extended. But the thing about their visibility, can you go back to that one with that really, like the UFO one with the prominence underneath it? It looks like a UFO refueling on the sun. It was like your second slide. One slide. I think the most visible angle is a great circle on the sun. If you have a cavity that happens to be angled right along the great circle of the sun, there it is on the left. And you can kind of see that that filament that's coming down to it is kind of angled at the radial angle. But the ones that are persistent longest are the ones which are parallel to the equator, like a polar crown, because they just can be there for day after day after day, and they're still visible enough.
Mhm.
Thank you, Ula.
Thank you.